Hi, my name is Uwe Köckemann from University, and I'm here to present my paper titled The AI Domain Definition Language, 3 Use Cases for Integrated Planning, Reasoning, and Learning. Now, for this paper, I would like to view planning as piece of a puzzle in some kind of integrated system. So usually combined with some kind of other AI algorithms like learning or reasoning algorithms, or as part of some kind of framework that also includes execution with acting and sensing, or scheduling, or technology-specific bridges that connect our system to, for instance, the data provided by a user. And so while we're looking at these 3 use cases, the interesting question for me in this talk is how can we model everything in a single domain definition language? So we start by going over our 3 use cases and then talk about our design goals from there. And then I will talk a little bit about the language itself and then finally conclude. Now, the first case is using a planning system to support a learning system. Now, on the right side here, we see a more or less complete version of the flow chart, where the yellow boxes are some kind of algorithms. For instance, we see here a planning algorithm. The blue shapes are decision points. The orange shapes are loops. And the red shapes here are just the start and end points of the system. So in this case, we start by generating data goals. Then we plan to collect the data. Then we execute our plan to actually perform this data collection. And then in this small loop here, we see we run cross-validation. Finally, we calculate the accuracy. And then we do this until the accuracy of our model is good enough. So the idea is, ideally, if we were to generate goals here in a smart way, for example, taking inspiration from active learning, we can try to cover parts of our, we can try to gather data in which our model otherwise underperforms. The second case is learning for planning. So here the idea is we don't have operators to begin with. We just have an empty set of operators, but we have a goal and we have baseline actions that we can execute. And then if we currently have a plan, which in the beginning we don't, we execute the next action in the plan. Otherwise, we just execute the random action. And then we collect state transition data. We run a decision tree learning algorithm, and then we extract operators from the decision tree, essentially by creating conditions based on the decision points in the decision tree and effects based on the leaves of the tree, which describe the effects of that the action had on the state. And then we attempt to plan, and then there is a bit of management down there. So this here just continues in an infinite loop. So eventually, hopefully, our operator set will be complete. The third case is slightly different. So here we also have these green cylinders, which represent how the data is connected. Those were not included in the previous graph because this would make it a bit too complex. So here we have, for example, the initial state I, our set of operators O, signatures. And we also have a goal G, which is in the middle here because it's used by various components. And then we start by checking the goal, which means we test if the planner, so based on our operators here, can actually, based on the operators and signatures, actually can reach the goal. And based on the result of this test here, we generate a goal query, which can be trivial if the planner understands the goal, or it can be something more complex, which would then require us to derive a reachable goal from the goal that was given. An example is, for instance, if let's say our goal is to go to the kitchen, but our planner only understands location A, B, and C, then this goal inference step could, for instance, use a knowledge base that knows that location B is a kitchen, and therefore change the goal to the change the goal to the robot should be at location B. And then if everything goes well, finally we plan to create a plan, and then we stop. So we can easily create a lot more cases like this. It's very easy to come up with these examples. Slightly different thing would be to integrate planning with resources. Otherwise, there's a lot of ways of combining planning and learning together if you look at the literature. And here you could have a more open-ended thing where you plan to gather data, to learn, again, to improve your planning model and so on. That this becomes more of an online algorithm that then also has maybe some other goals that need to be reached while this is happening. And then if you have some drawbacks or some flaws in your domain that should be fixed by this algorithm. Other examples include integrated task and motion planning or various combinations of the above. Now, one of the things I would like to address with what I'm proposing in this talk is how we can make it easier to build such systems. So on this end, I would like to have some sort of well-defined integration. So can we, how can we build systems ideally as easily as putting these figures together that are shown in the beginning? One of the other goals is simplicity. So if I want to create a simple integration, then it should also lead to a simple model of this integration. Reusability. We already saw in the previous figures that, for example, the planner appeared in all three of them. So I would like to just reuse the same planning system or the same planning component. This then also can lead to robustness because if we use the same component in a lot of different contexts, ultimately that means that this component should be very well tested. And we can also test components more by themselves as we break things apart like this. And freedom in the sense that I don't want to impose any specific way of solving a problem. This should be up to our imagination. Now, for this, I came up with the AI domain definition language framework, which is both a domain definition language, which can be used to define types, models, and data, and this kind of assembly of systems, as we have seen earlier, and a set of libraries. So a core library, which can parse the language, covers the basic representation and basic functions, and just gives you some infrastructure to work with. A common library, which includes types and functions for a variety of AI subtopics, as well as example libraries for integrated AI, which basically are exactly the implementations of the three cases that I have shown, and external libraries to connect to existing AI libraries for state-of-the-art implementations. Now here's a quick overview of what the language looks like. Basically, everything is represented as a term, which can then be, for instance, a variable, a symbol, or a more complex thing like a tuple or a collection. And then the files themselves are composed of entries, which all consist of a type, a name, and a value. So here's a type, could be a planning problem. The name could be a symbolic handle on that problem, and then the value is the problem itself, including the initial state, goal, and a set of operators. Now on the framework side, here is a quick overview, which also includes the core and the language to see how everything plays together. So the core library but also the common example library are written in specific programming languages. So currently we have Java, Python, and Scala libraries. And then here we can see, for instance, as part of the language, we have the types that we define, models and data. We can also write functions within the language itself, if that's useful. And also requests, which is what we will use to bring these flow charts that I showed earlier together. And then here we see in the common library, we have a couple of well-known AI areas covered, like planning, satisfiability, constraint processing, constraint optimization, and then our examples. Now, if we take this and look back at our 3 use cases, we already saw that we have a lot of components that are shared between them. For instance, planning, learning, action, execution. And then we have some kind of glue components which connect, for example, planning and learning together by extracting operators from state transitions, extracting data from state transitions and then operators from a decision tree and so on. And then we have some kind of wiring through function calls, loops, sequences, and so on. So all of this can be represented in AIDDL directly via requests. On the right side here, we see an example request just to show what it looks like inside. And this is part of the learning for planning example, where we ultimately extract our data, then get our decision tree, and then we generate operators from this. And what's really nice about this is that we end up with a single language for our AI models, our data, and the integration itself. So I think this will lead to some very interesting possibilities in studying these kind of integrations in a more detailed way. So in future work, I would like to study the integration and hybrid aspects more deeply. I'd also like to look more into hybrid planning, which I've done in the past as well, but I think this will allow me a more thorough study of this. Another really interesting thing that this opens up is possibilities in auto AI. So for instance, using planning to assemble these kind of sequential requests that we saw before. So if each call in this sequence here on the right side is an operator, then maybe we don't have to write the sequence ourselves. We can just generate it in a goal-based way. And of course, easier assembly. So ideally, I would like to put an assembled system together by just dragging and dropping into some graphical user interface, and then basically having this model written for me behind the scenes. That's my talk. Thank you very much. And let me know if you have any questions.